So I am James Poe with Carnegie Mellon University, and I think those of you who've been coming to the seminar also know that I'm one of the PIs in the Intel VMware Crossroads 3D FPGA Academic Research Center. I hope it's an interesting talk. So what I want to talk about is this question: how hard is it to use FPGA, in particular, to accelerate computing in 2023? The genesis of this work is actually a project I personally started. So in this talk, I'm going to use first person I, because I actually did this. And it's this, from the experience I gained, I want to touch on this question and talk about what it could be. So I just get right started, okay? And oops, why is it not advancing? Okay, so it is a high-level synthesis talk. I consider myself a cheerleader, a champion of high-level synthesis. And to begin the talk, I want to kind of level set everyone's expectation. So this is my HLS manifesto, right? I think I want people to have to write the proper, correct expectations on what HLS is about, what it can do, and how to use it. So number one, first is on the right prompts, HLS absolutely can produce high quality results, as good as RTL. And I think it's just that people have to realize, right? Not everything is meant to run on hardware, run as hardware, can be made better in hardware. In those problems, it doesn't matter use RTL or HLS. It's not HLS' fault. Now, of the set of problems that does have the potential to work well in hardware, given the right designer, somebody who knows how to use HLS, again, absolutely can match the quality of RTL. This is something I experienced personally. And what it is, when it comes to performance, how you write C code matters. And this is something, if you did high performance software, it's the same thing, right? You want performance, you have to write the program correctly. And so I think the bottom line is that that's the takeaway. This is my understanding. Right? HLS, at the end of the day, is a compiler. The performance has to be in the program for the HLS to find it. And the programmer is the one that puts it in the program. So if HLS doesn't do a good job, it's usually the programmer's fault. So with that, we'll get started. Okay, so this is the question I asked at the beginning is slightly facetious, right? How hard is it to use FPGA in 2023? This is a very easy answer, right? It's no harder than using GPUs through CUDA or OpenCL. I don't know if you kept up with kind of the latest technology, right? The latest, OpenCL is being replaced by the new SICO standard. Intel DPC++ together with oneAPI is an implementation of such a thing. So this is in this new standard. This is what's called a single source heterogeneous programming. And today, to use DPC++ with oneAPI to program and use an FPGA in a system, it is literally no harder than writing main.cpp. You call ICPX with a little bit of magic incantation, but this is effectively GCC. You compile, and once you compile, it is as easy as saying a.out, the program runs. And when you run this program, something runs on the CPU, something runs on the FPGA, and actually, right, the SICO DPC++, it's not an FPGA language. This is a heterogeneous language, and the same program should work functionally. Right? Functionally, it should be portable across many systems with many different heterogeneous extraction targets. So in that sense, right, it is not, there's no question that if you want to run a program, it is no harder, okay? Because it is the same thing you would do to use GPU if you were running through CUDA or OpenCL. But with what I said on the last slide, the thing we understand, right, functionally portable is one thing. When you want good performance, that always involves human enhanced. And that, I remind you, is always the case. You want performance on GPU through CUDA and OpenCL, that is also not easy. And I don't think getting performance out of FPGA through SYCL to OpenCL is any harder than that. So I think there's no harder than, it's a fair statement. Now, I will give GPU one thing. Because you think about it, when most people who use GPU computing, they're not writing CUDA, they're not writing OpenCL, right? They're usually working something much, much higher level, right? TensorFlow, Python, and the way they interact with GPUs is actually through these performance libraries that hides everything underneath. So with a very high level abstraction, they are able to access performance. That is something that we don't see in FPGA as much, but maybe there's a way to get there as well. So that's something that I want to get to today. Okay, so this question, is easy, but I think there is a serious question behind it if we sharpen the question a little bit. So it's not asking blanketly how easy, right? Let's narrow it down. We care about performance. How hard is it to get performance on FPGA? Does using SYCL high-level synthesis impede with your ability to get performance? And also, we want to separate different kinds of programmers. There are the nuts and bolts programmers that are developing high-performance IP, developing kernels. But then we also want to think about the application level people. These are people who create useful functions. They're not into building performance in the kernels, but they are the ones that can actually do useful things with it. And how easy is it for them to access functionality and performance through developed kernels. And lastly, right, performance not only is specific to the programmer, it is also specific to applications. So I think choice application domain also matters. So one of the questions I want to get to the end is, right, if FPGAs become easy to use, where do we actually use it? Where's the best place to actually use it for its full advantage? And that's the real question we're going to try to explore today. Okay? So with that, we'll get right started into the real part of the talk. So to kind of go through the first part, I want to just introduce a design example. Okay? It's a simple example. It's almost a toy example. And so the example I worked on in the last few weeks is the problem aggregation. This is something I'm actually planning on building for my course, use this teaching material. Turns out to be very, very interesting. And if you're not familiar, so this is an important database analytical data query kernel. And the basic problem is this. I give you a string of key value pairs. All right, and goes as long as you want. What you're looking for is at the end of the string, you need to tell me which are the distinct keys that appear in the string. And then for each the key that appeared, I want a summary, right? I want their value summarized somehow. It could be a simple arithmetic sum, could be a minimum, could be average, something like that, okay? And so in that simple problem, the way you visualize it is a string comes in and we're doing accumulation in a table. And so somewhere there is a map table that takes a key, maps it into an index, and using this index, we're able to perform the accumulation on a linear table. And so you can think of the hash table, you can think this is like uninterruptible memory. This is how you would visualize this conceptually at least. Okay. On an online talk, it's a little bit difficult to see people's faces. So if there's something very off, you should stop me and I'll answer questions. I don't mind. Okay. Now, this is the problem posed. To actually now go about building this, we got to nail down a few more details. So, to make it a little bit more precise, let's just go with, say the keys are 32-bit integers for both the key and value. Could be other things, right? But let's just go with 32-bit integer keys and values, and we'll just use a simple addition for aggregation, for accumulation, just keep it simple. Now, one thing that is a choice is that an assumption I will make is I know, right? The information I'm given up front is I know at most how many distinct keys to expect. So this is not a way to make the problem easy. If you look in databases, you look at database benchmark, it is in fact that more than half of the queries are these small size with small number of distinct keys. So 64 is a good number for this. And of course, it's not always less than 64. So at the end, I will come back and address what happened when it's bigger than 64, when it's much bigger than 64. And the thing you should appreciate right now is you wouldn't build it the same way. Okay? So for the current problem, we're talking about a small aggregation of 64, at most 64, or some number parameterized up to 64. Now, we're doing hardware. We want performance. So what we like to do is actually be able to process n number of key pair value per cycle. And this is to achieve the desired throughput. Number you can imagine would be anywhere from 1 to even up to 32. So going back to the previous picture, what we have seen now is, right, this map table is, besides doing mapping, we need to actually map parallel multiple keys. And to do accumulation, we need to in parallel do multiple accumulations. Possible, okay? And so, this is one step further. Now, one thing you already see is mapping. That is going to be a hard problem. The thing that jumps out more right now is when I start doing n-way accumulation, then something that table begins to take on the detail that I need to do n reads, n writes. So as a hardware person, thinking a little bit, you will come around and say, I think I can do better. So instead of building a n read, n write table on an FPGA, this will mean I build it out of registers. What I can do is build in one read, one write banks. And then I directly accumulate per lane its accumulation. And so this bank will be redundant, but now I can use block RAM. It is actually much faster, much cheaper. And only at the end, when I need to read out the results, I need to remember to read across all of them to produce a total sum. And so this is something that we as hardware designer would think about. And this is something that you will have no trouble expressing in high-level synthesis. What's left here is this picture, okay? This the map table, which will become some kind of content addressable memory. And this, if you think about it, is the hard part. And so I'm going to try to work through this problem in the next few slides. And hopefully, if you agree with me, if I can solve this problem well, like the rest of the problem is solvable. In fact, you should believe me because this all exists. It is solvable and it can be solved very, very well. So that's dive right in at this content and addressable memory. So remember, what I want to do is present it with n keys. I want to be able to n keys per cycle produce n mappings per cycle. So to get started, we can write fairly literal C code, okay? And what you see here, I'll explain it. You don't have to read it. It's not hard to understand as I explain it. So up here, I'm declaring essentially the CAM table, the content addressable tables. So I'm going to have G keys, and there's a valid bit for each of them. Kind of, we can skip forward. Kind of the upper part of the program is right here, right? So if you read that code, what we're doing is we're going to take all keys. We're going to iterate over all keys, compared to all CAM remember keys. We're going to compare all of them. And if I find a match, then I found a translation. Okay? So this is this is the content addressable memory you imagine. And for input, I'm going to take it compared to every single location in this CAM array. And if I have multiple keys, I'm going to take each input and at the same time compare to all the CAM array. And if I'm lucky, well, if the key exists, there we go. We found the mapping. Now, for you to see a key for the first time, you will not hit. And so after this first step, there's the second step where, for all the inputs I didn't hit, we need to allocate a new entry in the CAM, and this new allocation becomes the indice for this mapping. Okay, so hopefully, you at least believe me that this is the correct C code. It's not that tricky. But what's more important is that the C code, when you take it through high-level synthesis, in the way as we're building a streaming implementation, right? This function is going to be called inside an infinite loop, and inside this infinite loop is going on every cycle. In SYCL, there's a construct called a pipe. It's essentially a FIFO-like thing. So on every cycle, we're going to pop out n input keys. We're going to call this function, and then in the program, we call the function, and the result we're going to push downwards into the next level. Okay, and so this is what a streaming stage will look like. Now, when you write this function, this is a very sequential-looking function, and as you read it, that's a part of the sequential that makes it easy to understand. When you hand this over to the compiler, what will happen is, because I'm calling this in a loop, and because the structure of the program of this function, the compiler is going to try to pipeline this. Okay, so to pipeline this, the internal for loop, these for loops, they will all become unrolled. So all the resources become parallel, become explicit, and then for the loop body become pipeline, so you can have multiple iterations that happens in overlap. Okay, and I think I already mentioned before, right? So we have, this is the CAM array. The CAM array, needs to be accessed by n keys. All entry CAM array are accessed by all keys at the same time, and this, of course, it becomes a very expensive register-based implementation to support the concurrent access. For this program, for this function, right, the compiler can find a very good schedule. Very good means you can pipeline it, you hit a high frequency, and it is able to begin a new iteration every cycle. Now, this is one of those trivial pipelines. If you look over here, right, there is a feedback. On every iteration, there is the potential of you changing the state, and then the next iteration reads the state. So this is something with dependency. So in order to hit the one iteration per cycle, the compiler actually had to schedule the pipeline correctly to have that feedback happen in the right place. And if we look at this specifically, right, so the critical part of this pipeline synthesis is this read, modify, write. Okay, and so in the reading part, we're checking all inputs against all keys in the CAM array, and the writing part is when there's no match, then we need to allocate. Okay, and this needs to be fed back to the next iteration in the next cycle to be consumed. Okay, now this, if so for that, this becomes the deciding critical path in the pipeline. If you wrote this and sent it to SYCL, what you see is that the critical path delay is about 6 nanoseconds. It's actually, when I first saw it, at 6 nanoseconds, I should point out, is for n equal to 4 and g equal to 64. Of course, it depends on what those numbers are. But if you think about it, I was very surprised how much I can actually pack into 6 nanoseconds. But 6 nanoseconds, at the end of the day, right, we're talking about maybe 160, 170 megahertz. Right? As hardware person, in today's FPGA, we should try to do better. Okay. One thing I will point out is that, right, the way I presented this, I showed you code. I showed you code, and I explained to you what things look like. That's not how I design things. I'm a hardware designer. The way I designed this, I first had the picture in my head. With the picture in my head, I wrote the code. That's the way it has to work. Now, what's important to point out, right? I have the picture in my head because I'm using high-level synthesis. The picture in my head is at this level of detail. I do not need to get down to wire cycle bits of RTL. I'm able to operate at this level of abstraction, write this code, and have confidence in the compiler that it will do a good job. Okay, so it did a good job. It came out with 6 nanoseconds, but that is my fault. This is why I asked it to. So I need to do better. Now I put on my hardware designer hat again. And I say, the critical path, I would like to cut it. So what I like to do is, right, I have a large content addressable memory made out of register that's slow. And to do a remodify in one cycle, that's my critical path. It would be very nice if I can delay that update by 1 cycle. Okay, if I delay the update by 1 cycle, then my critical path will improve. However, right, when you have feedback to the next iteration, if you create this cycle, you create a rot hazard. If you did this naively, your pipeline will stall every other cycle, or your iteration interval will become 2. The frequency goes up, the rate goes down by half, nothing came out of it. So we have to think a little bit harder. And for those of you who have taken computer architecture at some point in time, you would know this trick, right? So what you want to do is memorize, okay? So I wanted to update the big table in 2 cycles. I have a raw dependency I need to resolve every cycle. So what I can do is I can create a small table. It's an n-entry scratch pad. So on every cycle, when I have a new update, instead of updating the big table in the same iteration, I update the small table in the same iteration. And with that, right, for the next iteration, the big table will be 1 cycle behind, but together with the small table, it is all current. Okay, so when I update the small table, I defer the big table write by 1 cycle. When I check the big table, then I check the small table. If I do that, it's all consistent, and I am able to almost cut the critical path in half. So now, right, previous was 6 nanoseconds. Now we're at 3.7 nanoseconds. Okay, for the same n equals 4, g equals 64. Okay, so that's my math is not very good anymore. 250, 270 megahertz maybe, right? But call 250. This is 1 giga pair per second, right? Each pair is 8 bytes. Okay, so this is what the hardware person says. And with this picture, now I just need to tell the compiler to go ahead and do it for me. I'll just show you the code. This is, you don't have to really read it, but if I point it out, it's not too hard to understand. So here, right, this is what we saw before. This part is the part where we're taking all the input keys to compare against all the CAM registers. That's the same thing as before. What you see new is, right, I've introduced this new state. That's the scratch pad. And after checking the big table, I have to check against the small table. And that gives me the current information. Now, once I check the small table, this is where I'm updating the big table. And by doing it this order, right, this is now delayed, right? This update is happening 1 cycle after the value was created. So this is where the defer update happens. And what you notice here is this is the part where on the previous version, we're directly updating the CAM. Now we're updating these scratch pads. and the real update happens in the next iteration. Okay, so here I just want to give you an example. I can make the slides available if you want to double check me, but this is what this picture shows. This is only a giga, and we're hardware people, we're not satisfied with this. So can we do better? Of course, otherwise we wouldn't be given this talk. This is my third try. And having done this a few times, look at several different ways, I remember we're streaming. When you do streaming, latency doesn't matter. It is about throughput, okay? So in that case, to do this content addressable lookup, there's no reason to look up in parallel to get an answer very quickly. What I can do is actually, for each iteration, perform the content, the CAM register check sequentially, one after the other. All right, so for each iteration, now it's happening over a very long latency. However many keys you have, it's stretched out over many cycles. Now, it is a pipeline, and we have a very long string. This pipeline is full. So this long pipeline is now filled by as many iterations as the pipeline is deep. And right, the structures are doing the same number of comparison per cycle. Just previously, we're doing all the comparison for one iteration per cycle. Now I'm doing the same number of comparisons, but for G iterations at the same time. Okay, so I'm kind of twisting, imposing a different structure and timing to the computation. The same computation has to happen, but I can control how I want it to happen and where things happen. If you do this, what you see is that now the critical path becomes a localized thing. That remodified writes no longer against a big table, it's only per stage against its local key. Okay, and if you did that on the FPGA, we had this is a Aggregation 014, we can get under 2 nanoseconds. All right, and what's even interesting is this is actually not very obvious. This 2 nanosecond, it doesn't matter how big G is, it doesn't even matter how big N is, because of compiler pipelines. The only limit is it gets expensive, right? So there is an N square part to the cost component. You wouldn't build very big aggregations this way, but for up to 64, right? This is effective, and you can, for all practical numbers of G and N, you can hit this 500 megahertz target frequency. So the FPGA, we have a this is the thoracic board that we use. This is, I think, the second smallest FPGA that they have. That's on the second smallest Aggregation FPGA. On this thing, for G equals 64, we can max out that board at over 20 gigapairs per second. So this is 20 times better than what we did before. And what I did is I thought about things correctly, right? And just to kind of put it in context, 20 gigapair, that's 160 gigabytes per second, right? There's nothing on this board that can give me 160 gigabytes per second. I can process things way faster than can actually get I/O onto this FPGA. So that's a different problem we have to address somewhere else. But again, the designer design. And then I tell the compiler, do it for me. This is actually a little bit interesting. So as I mentioned, the same computation has to happen. And if you look at the code, they're actually very, very similar. However, there's subtle differences in how dependencies are formed. It creates a different imposition on timing and structure. Now, one thing that's very interesting is this is actually the simplest piece of code, right? The highest performing code is actually the simplest looking code. So I think there is something to, good designs are simple designs. Simple designs are pretty designs. But put that aside, right? So if I write this, I will get the pipeline I showed you, and it's actually much more intricate than you might imagine, because these are not single stages. These are at themselves pipeline. And you have to think about why is it and doesn't matter, because because the pipeline is happening. Okay, but coming back to the point, I showed you 3 tries, right? From the first try to the second try. I imagine a very special compiler might be able to automatically infer transform 1 to 2. For the third, I don't think any compiler will be able to do that. Okay, and so this is the point that where I say the programmer has to be able to put the performance into the program. What's most important is the language and compiler doesn't impede in my ability to put the performance into the program. And in fact, the compiler doesn't impede, it actually helps, right? So where it helped is it made it not painful to design hardware. And I showed you 3 tries, I probably did 20, 30 tries. Small variations, but with HLS, I'm able to try them very, very quickly. And HLS, there's the front-end feedback. I can get feedback on the order of minutes. I don't have to wait hours to get feedback. And that feels very much like compiler optimization, high-performance programming. And so that's kind of all part and parcel of today's high-level synthesis. Okay, so let me move up a little bit. So what we're focusing on is that one kernel, right? A kernel doesn't make an application. So we're talking about an application. And SYCL is a full system language. So as we talk about this kernel, the kernel exists in an application. The application exists in the system. So in the SYCL language, it's a lot like OpenCL, right? There's an environment that the program lives in. So there is a host CPU. Host CPU has host memory. You have devices. In our case, it's the FPGA. And you can have local DRAM to the FPGA. As part of the language, there are various facilities that allows you to communicate between the host and the fabric. You can do the classic DMA. Nowadays, it's a universal shared memory in a single address space. You cannot reach out and touch each other's memory. In SYCL, one thing, because of being streaming, one thing we use a lot is these pipes. Okay, so pipes, it's a FIFO abstraction. On the fabric side, they're actually FIFOs. They're actually very cheap FIFOs. But I can also extend pipes across between hardware and software. On the hardware side, it's still FIFO. On the software side, it's an InQ DQ kind of interface. But it's for streaming, it's a very convenient. It is a high performance interface. So it's in this environment, I'm instantiating my IP. I'm instantiating my IP to create the application. Now, you have to now imagine I had built the rest of the IPs, and you have to believe me that I can do it, and they're good. So there we go, right? So these are the kind of 3 pieces of IP I would need. There's the map, there's the aggregate, there's a little bit of pre-processing I need to do to make it all work correctly. So 3 IPs that are written in that streaming style. And because they're streaming, they can be easily connected, even allowing for parameterization of width and performance. Right? These SYCL pipes allow them to be very plug and play. To build an application, right? What I'm showing you is actually now no longer high-level synthesis. Well, it's part high-level synthesis, but at this point, I'm operating in that main.cpp. And to instantiate these IPs and to stitch them together into a program, an application, right? This thing I'm showing you is lines, very few lines of code in main.cpp, right? Provided someone else built you these high-performance, efficient kernels to put them together to do something interesting, we're talking about a few lines of C code in main.cpp. In fact, right, we build this will run. If this doesn't run fast enough, I want more, right? I can, with a few more lines of C code, I can double the pipeline, introduce a bit of C code to do the fork and join, and I can change the performance, change the design of my implementation. All this is done at a very high level of abstraction, and the performance is locked in by how well you built these kernels. One thing I mentioned, right? So this is for small G's. What if I want to do very big G's? In fact, let's be, let's be extravagant. 1 million, that's a lot, okay? We wouldn't build it the same way, of course, but there's a way to do this. If you actually had 1 million key randomly distributed, there's another way to build it. Here, to do this in hardware, you have to give me something. And the thing I'm asking for is, right, the keys have locality. So the thing I want to assume is, right, the keys have a working set that's a size that I can contain on an FPGA. The working set can drift, but I need to be able to capture the working set. So if you give me that, I can offer you this solution. Here really involves, again, using the same IPs, writing different lines of C code in main.cpp. What I've done here is I instantiate 4 copies of the aggregation pipeline, and the goal is to create maybe twice the capacity of the keys I need, okay? And I create 4 copies, not for performance. I'm gonna just bucket sort, bin the keys to distribute it, to spread out the load a little bit, okay? And so, as you start running, while the working set stays under, is captured, this will work very well. And as the working set start to drip, because I over buffered it, I can capture the moving working set for at least a little while, including also the kind of the random kind of the outliers, even during the working set. Now, at some point, I'm gonna run out of capacity. So one thing, a feature of the map table is that when it sees a key that is no longer able to map, it overflows. And what it does, it will send that key to the host. These are expected to be rare. The host will do the accumulation temporarily. And we can actually keep going until the working set actually drifts out of range. Then, the working set begin to overflow, then the host gets too busy. At that point, what do you do? At that point, pure software. The thing you should do, you should stop the computation, read out the current count, and just start over again. And then you can, again, recapture the new working set. And so using the same IP with lines of C code, I am able to build something at a very different scale. And here, I just want to kind of show the utility of this single source heterogeneous programming environment. But this is not where I want to get to, actually, right? So aggregate is not an application, it's a query. So ideally, what I want those Python libraries. What I want is, at the end, I want to create a library of these data queries, so that not only you can build aggregates, you can actually build whole queries. You can program queries, and this should be doable by someone who's not like me, maybe more like Janesh, who's been asking very good questions. Okay, so to recap so far, okay? So far, what I showed you is indeed using DPC plus oneAPI, I am able to do very well in streaming aggregation as an example, right? And my experience has been, it is orders of magnitude easier. It's not exactly easy, but it's easier than doing it in RTL. And I do not believe there are practical limitations to how well you can do compared to what you can do in RTL. In fact, if you really want to have the perfect final version RTL, you should still do what I do in SYCL. You lock in the final one in RTL. You don't want to do step 1, 2, 3 in RTL. That's not the right thing. The other thing that was surprising that I saw at the end is, once I'm done, if I look at the IPs, these IPs are much, much more readable, right? So in terms of maintainability and reusability, because of high-level synthesis, the code is very concise and it's very powerfully parameterized. And then because I'm using SQL pipes, these modules plug and play automatically through the compiler, including varying parameterizations. And lastly, partly just because it's kind of built into the SQL, the language, I have to do software engineering. I cannot ignore it. And so this whole plug and play modularity kind of just comes with. Now, the last thing I really want to push is, right, I think with all this, there is the potential to now build the library that I want and to be able to support application developers to also use FPGAs without my help. They just need my library, okay? And as today, like if I showed you the code, just like I showed you in examples, they're not easy to write. You have to write the right way, but I think many people can read it and understand what's going on. And to make small changes to it that doesn't involve timing and structure, I think a lot of people can. And also, now to actually use it to construct things, I think this library approach has a lot of promise. Okay, so hopefully it convinces you that you can use DPC plus SQL in streaming data analytics very powerfully. And that just leads right up to this last question, right? What is it good for? So don't be surprised. The answer I'm looking for is streaming data processing. I think this is where the killer app is for FPGAs used in this way. And the way I'm going to convince you, I'm going to tell you the story of Pigasus. And people with English processing know about Pigasus. Right? So Pigasus is this FPGA accelerated deep packet inspection intrusion detection prevention system. And the claim to fame is we can do 100 gigabit per second with one FPGA plus a little bit of CPU, and we can check every byte. This is deep packet inspection, so every byte is checked against the Schnorr rule set. Compared, the state-of-the-art software, you're going to get about 1 gigabit per second per core. So the comparison is, right, you can do Pigasus in a basic server versus some gigantic network appliance with hundreds and hundreds of cores to match the same performance. So in the digest, this is what Pigasus is about. It is a very hard problem with CPU and GPU, right? If you think about the kind of deep packet inspection, the rules with string matching, regular expressions, it has lots and lots of parallelism, but it's very, very fine-grained. It's irregular. These are not the kind of things that will map well to CPU or GPU. But it is something that's very important, right? Both in terms of throughput, we need to, for intrusion prevention, we need to run at line rate. And for intrusion prevention, we actually have to decide quickly enough to stop the packet. So latency matters. So, even if you can come up with a throughput mapping for a GPU, you cannot solve the latency problem on the GPU. So this turns out to be a very nice problem. And we found a very, my student Zapen Zhao, found a very, very nice solution on the FPGA. Okay. This is not a Pigasus talk. So I'm not going to tell you about details. If interested, you can read this paper. I'm going to tell you the rest of the story. The rest of the story is a sad story. So Pigasus we published in 2020. And when we published it, we open sourced the entire thing. And created a lot of excitement. A lot of people came to talk to us. A lot of people downloaded it. Several people actually went through trouble of rebuilding it as is, okay? And there were even a couple of attempts, people were trying to port the design to Xilinx. As far as we know, no one really continued to build it. Okay? It's open source, but it's kind of dead open source. No one's working on it, not other people, not even us. So why did this great project die? Because if you go to the GitHub, it's 80,000 lines of code. And even for us, ourselves, we don't understand it. My student graduated, no one knows what's going on. And with RTL, you touch one place, who knows what it breaks somewhere else. And so all together, it just required too much, right? The requirement on algorithm expertise and RTL expertise is kind of all melded together. You need that perfect, the perfect person like my students at Penn to be able to do something. And it's not that he did a bad job, he did a great job. You know, he can do magic with it. It's just when he graduated, all the magic left with him, and the project just set open and dead. Okay, and it's kind of, I just, you know, as good as this is, RTL is a problem. And so to bring things back, now the rest of the story is a good story. So this summer, so I mentioned that I did a pet project, and what I did is I began to rebuild Pigasus using SYCL DPC++ in HLS. Okay, at this point, you know, I have completed the peak packet inspection part of the stage, and I can show you it's same speed, same cost as RTL. If you know how to use it, there's no reason to not expect to get the same speed and cost. I mean, that's really the way you should be thinking about it. I didn't do this part because I don't have to. Talking to the host is now just part of SYCL. There's nothing for me to build. There's no DMA, there's no buffering. I just use SYCL the language. On this side, there's kind of the network-facing part. I haven't done it yet, but maybe I won't, right? This part is a program. This part is hardware. This part doesn't change. So since I have good RTL, maybe I'll just keep the RTL. And you know, so I practically am almost finished. The hardest part is actually getting Ethernet onto my FPGA board. But this is something that we're taking on, and I think we will finish this, and we will re-open source this version of Pigasus, and hopefully this version of Pigasus will live on as a real open source project, and lots of people would jump in and help to build it, make it better. And for my own, besides Pigasus, what I also see is all these things are done in a way individually, they're IPs, and they are data analytic IPs, string matching, various signature matching. So all these things, once I build Pigasus, I can retain IPs, maintain them, and use them towards a data analytic library to build other different powerful applications. And so this is all part of what my group are committed to behind now. Well, I'm committing my students behind it now. So, all right, so let me just wrap up now. So just lessons. Okay, so I think, right, where FPGA has tremendous promise and advantage is in streaming data processing, programmable, using program as FPGA as a programmable computing resource. I think this is one place. It is a valuable application, and this is the best way to do it. Right? So in here we include both, simple transformation, inspection, data analytic, and these, we have examples of it in the different things I built. And right, I believe, right, if FPGAs were easier to use, this is a killer app. This is something that we can enable many people to use FPGAs in a broad setting. So to make that happen, I think the important part, we need hardware people need to build IPs, but more important, the demand has to be there. Application people have to want to use FPGAs. And here I remind you, it's not a question, RTL, CUDA, SYCL. It's Python, it's TensorFlow. We need to meet them at the level they work. And the way we meet them is by providing libraries that delivers the ease and performance to them in a way that they don't have to think about. Okay. Separately, right, hardware people do need to build hardware, and we need to build hardware in a way that's maintainable and reusable. If we don't want the project to die like Pigasus, we want the project to grow, to expand, to carry forward, then I think high-level synthesis is inevitable. And I think software engineering is something that we have to actually be teaching to the designers and build it into both the language and the tool and plant it into the designer's mindset. And so, I spent about the summer working using DPC plus oneAPI. I think what I feel is, I think we have a very, very close answer. Right? I think DPC plus oneAPI for streaming data processing is very, very close to being the answer I'm looking for. So, I hope that I'll be able to, bring you the rest of the project and share the code with you, and then have more people join me in this effort.